This video is about thermistors. It corresponds to section 5.2 of Applied Analog Electronics. Thermistors are temperature sensors. They are semiconductor devices whose resistance varies with temperature. And the ones we'll be looking at are negative thermal coefficient sensors. That means that their resistance decreases as the temperature increases. There also exist positive thermal coefficient thermistors, but those tend not to be used as much for sensors. They have other applications. Let's take a look at a couple thermistors. I have here two thermistors. This is a very common sort of packaging for a thermistor, where it's basically just a little bead of semiconductor in some sort of sealing package and two wires coming out the end. This is a slightly different version. It's again got a bead of semiconductor, but here the wires and the thermistor are covered with an epoxy coating. And that epoxy coating is basically waterproof. Though they don't guarantee its waterproofness, it is, for our purposes, waterproof enough. You can dip this thermistor into liquid and not short things out. And these are the ones that we'll be using for our labs because that waterproof property means that we can stick them into a water bath and measure the temperature of a water bath with them. And water baths are a good way to keep a fairly constant temperature that we can measure with a thermometer and with a thermistor, and so calibrate the thermistors. The particular device that we're using there, this black one with the epoxy, has a part number that's quite long. It starts with NTC, which stands for negative thermal coefficient. Then there's LE 413 E2 103 F520L. That's a really long part number. And quite often you'll get part numbers that are long like this because each part of that encodes some properties of the part for the manufacturer so that they can then sort of unpack this thing to see, well, what do the different parts correspond to. And you don't really need to know how everything's unpacked, but the NTC I already mentioned, that's negative thermal coefficient. L means that the thing has leads, so it's not surface mount or something like that. The E413, that describes the fact that it's got wires that are 30 gauge wires and it's encapsulated in this epoxy coating. The E2 means that the ends of the wires here have been plated with a tin alloy so that they're easier to solder. The 103, that's one of the properties that actually matters to us. That's 10K ohms. 10K ohms at 25 degrees C. And that's one of the most important properties of the thermistor is what's its nominal resistance. And usually that's given at a particular temperature. 25 degrees C is a very common temperature to give the nominal resistance at. So that part of it is a very important part. The F52 is how long the leads are. They're 52 millimeters long. And then the 0L, sorry, the 520, including the 0, is the 52 millimeters. And the L at the end means that this thing has a low B value. What's B value? Well, let's take a look at the formula for how the resistance and temperature are related to each other. And the simplest version of this formula is what's called the B equation. And it can be written in a couple different ways. One of them is to say 1 over the temperature is 1 over some nominal temperature plus 1 over B times the natural log of the resistance over the nominal resistance. Now, T0 and RT0 are the same temperature, and T0 has to be in Kelvin because we're looking at an absolute temperature here. If you try to do it in Celsius, you'd get 1 over 0 at places, and it just doesn't work. So we've got to have T0 in Kelvin. And so the 25 degrees C here, we would have to convert to Kelvin to get T0, and the RTC is the 10 kiloohms here. So the B value, if you take a look at this thing, this is basically a linear equation for 1 over T as a linear function, or affine function, constant offset plus 1 over B times the natural log of this ratio. Okay, this formulation is a common one to use because it generalizes to more complicated functions where we can have terms other than just natural log here. If you turn this thing around, though, and say, well, what's the resistance as a function of the temperature, you would get that the resistance is RT0 times e to the b times 1 over t minus 1 over t0. And both of these are referred to as the B equation because there's this two parameters here, the B and the RT0, that determine the properties of this thing. And you notice that what this thing does is that as t increases, 1 over t gets smaller, so this exponent here gets smaller, and the overall resistance drops. There's another way I like to write this one, because the RT0 and the minus 1 over T0 here looks like there's two parameters there, when there's really only one parameter, because you can rewrite this thing as R equals, and now I'm going to take RT0 e to the minus 1 over T0 times e to the b over t. This number here is a constant. Both T0 and RT0 are constants, and I like to write that as R infinity, because that is what the value that R would have as the temperature went to infinity. Of course, if you took the temperature to infinity on a real thermistor, you melt it or burn it up. So this is just a mathematical model. It's not, gee, it really goes there. It's the asymptote that you would be approaching. Okay, so we've got several different versions of what's really the same equation. The R infinity is usually not given on data sheets. What's usually given is an RT0 for a particular T0. And like I say, that's usually given as resistance at 25 degrees C. If you want the R infinity value so that you have a simpler equation, you can just plug it in here. Okay, let's take a look at a real data sheet, and let's look at the data sheet for this particular part. Okay, so the data sheet has got a lot of data in it, and a lot of times people get confused, particularly since for most of you this will be the first time looking at a data sheet. There's features here. This is basically advertising copy. There's nothing in this part that is guaranteed, though it is sort of why you might choose this part over some other part. The quick reference data here is a summary of more detailed information that is given elsewhere in the data sheet in more detail. And if you notice, the resistance value here at 25 degrees C is given as 4.7K to 100K ohms, a huge range of different resistances. That's because this data sheet is not just for the single part that we have. This is for the entire family of parts. And that's an important consideration, because if you just look at the data sheet and grab something off the data sheet, it may be for a different part. So you've got to be very careful that you're looking at the part of the data sheet for the particular part that you're dealing with. Same thing with the tolerance on the R25 value. This is how much fluctuation you get. Even if you got the temperature exactly right, how much fluctuation do you have on the resistance, the nominal resistance at that temperature? The B25/85 value, that is the B value that was needed for the formula, and the 2585 values there are referring to the particular way that they estimated that value for B. What we'll be doing in the lab for thermistors is using a different and more accurate way of estimating the B value. Okay, there's also things like operating temperature range at zero dissipation. Basically, this is what temperature can you use if you're not heating this thing up from self-heating. I mean, obviously, if you're running current through the resistor, then you're going to have power dissipated in the thermistor, and it's going to be heated up. And so there's a self-heating problem that you can get if you run any current through the thermistor. And so when they're talking about zero dissipation, this is saying, hey, if you're not running any current through it, so you're not getting any self-heating, what is the temperature range you can use this thing over? Talks about the accuracy of the temperature measurement, and notice it says for 1% types. There may be different types with different precisions. If we go back to an earlier thing on the tolerance on the R25 values, it was plus or minus 1% to plus or minus 5%. So here they're just talking about the 1%. Dissipation factors and response times, these have to do with the thermal properties of the thermistor. We won't be dealing with that in this class. We'll be looking at only sort of steady state behavior when the thermistor is at a constant temperature and isn't dissipating any power, or is in a equilibrium at any case. And then there's some other things about, climactic category, the minimum dielectric withstanding weight, things that we're not going to be dealing with in this class. Further down on this data sheet, there is a picture of the device and giving you the various dimensions of it physically, which you might care about a lot if you have to say, well, I have to fit it through this little hole, or how long are the leads? And notice that the length here, L, the overall length, is in the description of the different parts. And on the next page of the data sheet, we have a table of lots of different part numbers and corresponding to different R25 values, so different nominal resistances at that 25 degrees C. And then there's ones with different tolerances. Some of them have different B values, different tolerances on the B value, different lengths on the leads, and then what the part number is, and you can get it whether or not there's any lead basically in it, so that the RoHS compliant is there's no lead in it at all, and the RoHS compliant with exemption allows some lead in glass or ceramic. So they have different part numbers for all the different things here. The one that we were using is the 10 kilo ohm ones, the plus or minus 1%, the 3435K as the B value, the 1% tolerance on the B value, the 52 millimeter leads, and then it says RT table, table 3. Notice that there's 7 different tables there for the RT table. What are those RT tables? Well, here's table 1. We need table 3. So let's go down to table 3. Table 3 is for the 10 kilo ohm ones with the B3435K value. And those are the ones that we've been using in our labs. You should always make sure that the part numbers you have, you're looking at the correct one. Because if you tried to get the values on for this table from one of the other tables, like you looked at, oh, first table, resistance temperature, this is the one we want, that would have been for a different part and would not have been correct. So here we've got a table of measurements that they made, saying at that temperature, what is the resistance? What is the resistance compared to the R25 resistance, so that at 25 degrees C you get the 1 there. What's the tolerance on the resistance? Notice that because both the B value and the resistance have tolerance, it's going to be most accurate at 25 degrees C, where the B value doesn't matter because it's just what is R25. And as you get further away from 25 degrees C, you get worse and worse measurement. And so if you're trying to measure minus 40 degrees C with this device, your tolerance is going to be plus or minus 4% or 4.25%. And I'm not sure what the alpha value is here. I would have to perhaps read the rest of the data sheet to try and figure out what it corresponds to. The temperature tolerance is if you're converting this resistance back into temperature, how much error would you have in the temperature? Notice that because the resistance and the temperature are not linearly related, there was both a logarithm and a 1 over t involved in that, the tolerance on resistance may vary quite a bit without changing much the tolerance on the temperature. And if you take a look, what happens here is that the minimum error on temperature is again at the 0.27 because it only depends on the nominal resistance value, and it gets worse as you go off in both directions. But it gets worse on temperature at the high temperature faster than at the low temperature. So if you take a look at the resistor tolerance, it looks worse at the low temperature. If you look at the temperature tolerance, it looks worse at the high temperatures. But over the entire range, everything's going to be within plus or minus 1.38 degrees C. And then it gives you what the minimum and maximum values would be for that resistance, where it gave you the ideal value in column 2. The last two columns say what's the minimum and maximum if you have the worst case tolerances for both the resistance and the B value. Okay, so what else do we need to know about this? Not a lot. You're going to want to plot formulas like this. You might want to figure out, hey, given the values of the B value and the resistance, what is R infinity? So that you could write this equation down and plot it. Notice that when I've been given the B values, I've always been referring to it in terms of K. So it's 3435 K. That K is Kelvin. Because in order to do this exponentiation here, I really want to have a unitless number here. So B over T, both of them have to be in Kelvin. And R infinity here has got to be in ohms, so that we end up with ohms times a unitless thing is still in ohms. There are more complicated equations that get used for describing the behavior of thermistors. This B value, this B equation, is a very simple equation, and so it gets used a lot in describing thermistors. But if you measure the thermistor and measure the temperature accurately, measure the resistance accurately, you'll find it doesn't quite fit on a curve like this. And so there are more complicated models that can get used for modeling a thermistor. The B equation is a simple approximation to the actual behavior. A slightly more complicated formula does 1 over T is a constant plus another constant times the log of the resistance plus, and that should be that log of resistance there really should be divided by 1 ohms, so that you get a unitless thing here, plus A2 times log of R over 1 ohm, and then this log cubed. So this, if you notice, the first part of this thing looks just like our equation up here, except for that we've got a log of 1 over RT0 here that gets merged with 1 over T0 to make the A0 term. The A1 term corresponds to the 1 over B term here. The A2 term is the new one. Or actually, probably better to write that as A3, because it's the coefficient of a polynomial in the natural log of R, where you've got a cubed term. And this is sort of the next level of sophistication. It adds just one more new parameter. If A3 was 0, you could convert between the B equation and this one just by some simple change of variables. But if A3 is non-zero, then you can get a little bit of curvature to that 1 over t versus natural log of r line. And it is this equation, incidentally, is called the Steinhart-Hart equation, and it's a slightly more sophisticated model of the thermistor. It allows you to get a slightly more precise estimate of what the temperature is from the resistance, or vice versa. And we don't generally end up using this one in class because for what we're doing, the B equation is precise enough. But if you want to fit the Steinhart-Hart equation to your data, you can certainly do that and get slightly better fits as long as your measurements are really accurate. A lot of students have enough sloppiness in their measurements that the greater precision of this model is simply not justified. There's more noise in their data than the error in the simplified B model. And that's actually something that you can check after you've collected your own data is, do you really get a much better fit with this one, or is it just, all right, I can fit it. Obviously, if you've got more parameters, you can fit more precisely, but is the fit really justified, or are you just fitting noise? And that's something you have to look at for yourself once you've collected your data.